We're working in section 3.4. We're trying to graph polynomial functions. Let's start by asking the question, well, what can the graph of a polynomial look like? I've drawn out a few. You recognize the first two because they're the graphs of y equals x squared and then y equals x cubed. What else can a polynomial do besides this? Well, a polynomial can turn. And so in this next example, we start out like x cubed, and then we come to a turning point, and we turn back down, and then another turning point and back up. In fact, we can have as many turning points as we like. We can start up high, sort of like x squared here, and come down and then back up and down and back up. We know this is not the graph of x squared. We know that in order to have turning points, we're going to have a higher degree polynomial. But we'll get back to that later. At the moment, what we want to look at in each of these graphs is the end behavior. So the end behavior is the behavior of the graph as x approaches plus or minus infinity. So that's what happens at the ends of the graph, at the left end and the right end of the graph. And so in this first example, for y equals x squared, we can say that the end behavior is as x approaches infinity, what does y approach? Well, as x approaches infinity is going out to the right end of the graph, right? Positive infinity is to the right on the graph, and what's the curve doing? It's going up to positive infinity. So as x approaches positive infinity, y approaches positive infinity. And similarly, at the left end of the graph, x is approaching negative infinity this time to the left, and y is approaching positive infinity again. Y is approaching positive infinity again. So these are nice statements to be able to make about the end behavior. And then the other thing that we'd like to do is we'd like to just draw a little picture which would have the left arrow up and the right arrow up, and that's the end behavior. And there's a gap in the middle, and that gap in the middle represents all the mysterious things, all the turning points that might happen in between. So we're not talking about those right now, just talking about the left and the right ends of the graph. Let's try another one. Here I'll change the color on the pen so it's easier to see which writing goes with which problem. So now we're looking at something like y equals x cubed, and as we go out to the right end of the graph, as x approaches positive infinity, y approaches, well, what is y doing? It's going up to positive infinity. And as x approaches negative infinity, what is y doing? Y is going down this time. This time y is approaching negative infinity. And so we can draw a little picture that shows an arrow going down to the left and up to the right. And again, the gap in the middle means we're not talking about that behavior right now. There's an important observation right here that for any polynomial, the output y always approaches infinity or negative infinity as the input x approaches infinity or negative infinity. So we can always go out to the right end of the graph or the left end of the graph, right? That's the x direction. And then what are the y values doing? Either the y values are shooting up to positive infinity, giving us an up arrow like this one right here or this one right here, or the y values are shooting down like they are, for example, right here, shooting down to negative infinity. But there's only two possibilities at the two ends of the graph. Either y goes up to infinity or down to negative infinity. Okay, well, we need to figure out which it's going to be based on a given formula of a polynomial. So whether y approaches positive or negative infinity only depends on the leading term of the polynomial. Only depends on the leading term of the polynomial. So that's an important observation. Well, what the heck is a leading term? It's the term with the largest power of x. So let's go ahead and identify some leading terms and describe some end behavior. So in example 2, here are some functions. What does their end behavior look like? Well, let's start by identifying the leading term. In number 2a, f of x equals negative x cubed minus 4x squared plus 2x minus 1. The leading term is negative x cubed. The leading term is negative x cubed because 3 is the highest power on the variable. Maybe we should go through and get the leading terms for the other examples as well. In example 2b, do you see the leading term? 4x to the 7th. In part C, the leading term, 10x to the 6th. In part D, I tried to be a little sneaky. I put the terms in reverse order. I have the highest power of x all the way at the end. This time the leading term is negative 10x to the 4th. Okay, so what we said is that let's go back to example 2a. We said that we only have to look at negative x cubed. That means essentially that we can take the rest of this and forget about it. Okay, so what is the end behavior for negative x cubed? What is the end behavior for negative x cubed? Well, you know this because you know that x cubed looks like that. Here, I better clean this up just a little bit. So there's x cubed looks like that, and we need negative x cubed, so that would be a vertical reflection. So then that's y equals negative x cubed. And so our function, f of x, has the same end behavior as negative x cubed. What is that? At the left end of the graph, we're shooting up, and at the right end of the graph, we're shooting down. So we can put a box around that, and we're done. Let's go on to part B. This time the leading term is 4x to the 7th. So let's see here. Let's write 4x to the 7th. What does that look like? Well, x to the 7th looks like x cubed. So that's like that. And then if we multiply by 4, that doesn't change anything, right? That's just a vertical stretch. So we can say that the end behavior is here and here. At the left end of the graph, we're going down, and at the right end of the graph, we're going up. And we can box that up. For part C, we have 10x to the 6th. X to the 6th looks like x squared. And multiplying by 10 is another vertical stretch. It doesn't change the direction of the arrows. So we know our answer is this picture, this arrow, and this arrow. And so we can draw it here. We can draw an up arrow on the left and the right. One more. This time we found the leading term is negative 10x to the 4th. And so we can graph x to the fourth. And so multiplying by 10 doesn't change the shape, doesn't change the end behavior, but multiplying by that negative in front, it sure does. So actually, let me clean this up just a little bit. Let's label the green graph 10x to the fourth, and what we need is a vertical reflection. And so now, here is our leading term, negative 10x to the fourth, and it's pointing down at the left end and the right end of the graph. And so that's our end behavior. How does it look? Let's summarize what we just said. Let's think about this one more time. So the end behavior depends on the leading term, and specifically, when we look at the leading term, we're looking at the exponent. Is the exponent odd, or is the exponent even? If the exponent is odd, then we start out with something like x cubed. And if the exponent is even, we start out with something like x squared. And then the only other thing we're concerned about is the sign on the leading term. If the sign is negative, then we have to reflect that end behavior vertically. And if the exponent is positive, we can leave that end behavior the same. So let's summarize that let's summarize that, and then we'll be finished with the video. If n is even and a is greater than 0, then the end behavior looks like, well, if n is even, think n is 2, and if a is greater than 0, think a is 1. So you just talking about y equals 1 times x squared, and your end behavior is up at the left and the right. If n is even and a is less than 0, think of something like n is 2 and a is negative 1, or think of y equals negative x squared. And then with negative x squared, we've done a vertical reflection, and now the end behavior is pointing down at the left and the right. If n is odd and a is greater than 0, think of a function like y equals x cubed, and your end behavior is like this. If n is odd and a is negative, then think of a function like negative x cubed, and then your end behavior is up on the left and down on the right.